I'm going to be talking to you today about a study of faults in the Superior Province and its spatial relationship to gold mines. And my name is Jeff, as you know, and I work part-time for the data analytics section of Metal Earth. And I've been here about 2 years, I think. So I'd just like to acknowledge my co-authors, and there's many co-authors on this talk, and I thank you for your contributions. So just a little word about Metal Earth. The guiding principle is how do we integrate all the legacy data and the new data we've collected to assist in understanding fertile versus not so fertile greenstone belts. So the approach we're taking in the data analytics section is to do mineral potential mapping, MPM, or mineral prospectivity mapping, if you like to call it. And we've completed a number of studies you can see here, and some of this stuff has been published, so if you're interested in any of it, you can let me know and I can send you the copies of the paper. But today we're going to look at an ongoing study of the faults in the Superior Province. So the problem is we've got all this data, tremendous amount of data, and both 2D and 3D data. So how are we integrate it in a reasonably intelligent way to help the exploration community? So again, as I said, we're looking at mineral potential mapping using a GIS as our central core, and in this case we're using ArcGIS, and associated software called Nmap to do some of the machine learning language. But you can do that today quite easily with R or Python if you like. So here's our marching orders. We're looking for orogenic gold, and we all know the importance of east-west trending structures like the Destor-Porcupine and the Cadillac-Larder Lake fault systems for a spatial relationship with gold. And also other authors such as Paulson and Dubé have noticed that the splay faults from the major zones contain quartz veins, and the quartz veins contain gold. So this is kind of our marching orders. So we've got two study areas, the entire Superior Province, and we focused on an area in the Abitibi, and the reason for this will become evident in a few moments. So two study areas. So basically a summary before we start is we created two mineral potential maps, or mineral prospectivity maps, over the entire Superior, using just fault information and derivative from fault information like intersection density, etc., and I'll explain that shortly. And then we created 4 mineral potential maps or prospectivity maps in the Abitibi area. And we used random forest to produce 3 of them, and we used a weighted sum model, a knowledge-driven approach, to produce the other one, and I'll present this data for you. So it turns out that the mineral prospectivity maps that we produced over the Abitibi was our best performers from a statistical point of view, and I'll be showing that. And again, we used 2 machine learning languages, random forest, and a knowledge-based algorithm called weighted sum. So this is the core of our analysis. This is a compilation of faults over the Superior. We obtained this from OGS and from the Québec survey. But you will notice here that there's a clustering problem, and that the faults have been mapped in much greater detail over areas where there's more intense exploration. And that's going to create problems for us, unfortunately. So one solution we had is to look at mapping lineaments from enhanced airborne magnetic data, which you see on the right here. And this was created by making 3 shaded relief images and averaging those and making that modulate intensity in an IHS transform. And also we modulated the hue or the color of the image by the vertical gradient. So let's have a look at the predictor maps. We know we're looking for orogenic gold. What can be our vectors to orogenic gold mineralization? Well, what we're showing here on the left is north, south, northwest, southeast, northeast, southwest faults. And on the right, we're looking at east-west trending faults. So the way we processed this data was to put a zone of influence around each fault of 2 kilometers. Why 2 kilometers? Well, it's based on experience I have when I was helping Kevin Heather and John Eyre map in the Swayze Greenstone Belt. And we felt that the 2 kilometers would be an acceptable zone of influence, if you like. What I've done here in that little graph is just showing the number of gold mines as a function of distance for the east-west faults. So you can see there's a dip here, and that's at 1,500 meters, so perhaps that should have been used, but I went with the geological rationale in my discussions with various mapping geologists of that 2 kilometers. We also use fault density as a predictor map, and immediately you can see the effect of fault density here over areas where there's more intense mapping, more intense exploration. So note the clustering, and that's going to be a problematic for us. We also use intersection density, looking at east-west and northeast trending faults, the intersection density, and east-west and northwest trending faults. And the way we did this in ArcGIS is that we automatically generated a point at each intersection and then used a very small zone of influence to create a density map. And you can see here, the reason we didn't contour this fully is because we have a paucity of points in some of these areas here in the Hudson Bay lowlands. So we wanted to keep the zone of influence very, very small. You know, contouring data can be problematic, as we all know. For the Abitibi zone, we also integrated vertical gradient data magnetics. And what I did here is try to make a lineament map automatically from the magnetics. And you can see the linear structures, and you can see the pretty good correlation between the known gold mines and some of these anomalies, these linear anomalies. So that was the geophysics we used. We also used gravity, and here's the vertical gradient of gravity or vertical derivative. And what I did here was just slice the data to show zones of high density. And again, you can see the visual correlation between the gold mines and some of these high zones, if you like. So there's nothing wrong with looking at visually. I mean, we've all got brains that we can use. Well, mine's not so big, so maybe. But the key is what we like to do is quantify these relationships. And that's where the GIS comes in and the machine learning language comes in. Now, so we've covered some of the predictor maps we've used, but also for machine learning in a data-driven mode, we have to use training data with which to train our random forest algorithm. And what you're seeing here is we just chose 256 past and present mines. And you can see that in red. We didn't use the occurrences in this particular study, but this is our training data. So once we are finished with our predictor maps, we then can look at machine learning algorithms. And we heard a little bit about random forests yesterday. And random forest is a very popular and very powerful machine learning language. I use it all the time. And what it is, briefly, is instead of creating one decision tree, which can cause overfitting of the data, we create a forest of trees. You can see here, we can have a forest of trees, and the number of trees is actually chosen by you, the geologist. And I'll talk a bit about that in a minute. So that's a forest. Why random? Well, for each tree, we take the training data, and we take 2/3 for training the data, and 1/3 for validating the data. And this 1/3 of the training areas that we leave out is called out-of-bag samples. The other random issue that we look at is we don't build a tree with all the predictor maps. We take usually the square root of all the predictor maps. In this case, for the fault day, there was 8 predictor maps we used. And for when we included the geophysics, we had a total of 12. So we take, each tree is built from a random selection with replacement for each tree. And the reason we do that is you can imagine if we used the all predictor maps for each of the trees, the correlation between the trees would be very high, and we wouldn't get very good results. Our final map is a classification map and a probability map. And so the other advantage of random forest is it ranks the predictors. It tells us, and I won't go through how it does that because I just don't have time, but it ranks the predictors. It tells us what predictor maps are the most important with respect to our gold model. So that's random forest in a nutshell. It's a bit more complicated than that, but it's easier to understand, I think. Then we use the knowledge-driven model. And we usually use knowledge-driven models when we don't have enough training data. And what we did here is we created a weighted sum model. And you can see here the simple little equation. It's the mineral prospectivity map is a sum of each predictor map times the weight. And in this particular case, I weighted the data from 1 to 10, 1 being least important, 10 being the most important. And I'll tell you more about the weights shortly. So let's have a look at some of our mineral prospectivity maps. On the left, we see the MPM generated from the fault data. And there was 8 layers of fault information and derivative fault information. And you can immediately see a problem, the clustering effect here, as I said, where we have a problem with unequal mapping of faults, if you like. And this map is pretty generalized too, so it's not of much use. Here is the one on the magnetic data, and that looks more reasonable, but the statistics for this was very poor. So what the heck are we looking at here? I'm not sure. No, I'm only kidding. What we're looking at here is if we plot in these efficiency of classification curves, if we plot total area from high prospectivity to lower prospectivity against the percent of gold mines predicted, we get these banana-shaped curves. So I draw your attention to the red curve, which is based on the model, based on the faults, and the blue curve is based on the lineaments. So the way to read this curve is generally we're looking for banana-shaped curves, or a perfect predictor would actually have a curve up the y-axis and right across the x-axis. So this is how we validate our models, if you like. But the way to read this is at 10% of the area, the high prospectivity area, we are predicting about 80% of our mines, whereas the model based on the magnetic limits, it's down with a little higher than 50%. So in fact, this model is better, but we have that clustering issue. So possible solutions to our clustering, we looked at choosing a sub-area, and you can see the sub-area here, where there was more homogeneous mapping. We didn't have that clustering problem. And also we used a knowledge-based, as I said, a knowledge-based system to downweight our fault density. So let's have a look at some of these maps. This is the mineral potential map for our sub-area, our Abitibi area, produced using the faults, using random forest. Whereas on the right, what we see is another map that looks quite similar, but this is using our weighted sum model. So data-driven versus knowledge-driven here. And the similarity is quite striking. The correlation between these maps is about 0.82, which is pretty high. This little table is what I use to weight. Now, this can be somewhat subjective, but it allows the geologists to input their experience in terms of weighting. So, for example, I weighted, remember, from 1 to 10, I weighted the east-west trending structures as very important and the north-south structures as least important. All right, let's look what happens when we add the gravity data and when we add the gravity and mag data. You can see the similarities between the two. And good thing is we predict our known deposits, or gold mines, quite nicely. You can see here in this linear trend here. But we also have areas where we have no gold occurrences. So that's the beauty of this technique. It's been criticized because people say, well, you're just predicting what we already know. That's not the case, because we are predicting areas where there are no gold mines. And these are for exploration follow-up. Are these targets? I wouldn't say they're targets. I would say we're just narrowing down our area of search, but it still requires field work to go out and study some of these areas. So, also, as I said, we can look at the best predictors. What we've done here is we've taken the average of each of these maps that you can read for yourself here, and we look at highlighting the maps that give us the greatest prediction power. So we're looking at north, east, southwest faults are our best predictor, east-west faults, et cetera, We've downplayed fault density in our knowledge-based model. Note also that the vertical derivative, vertical gradient, is also a very good predictor. Now, in terms of validating our model, like we can produce a model, but how good is that model? So what we look at here is the red areas, and this is over the Abitibi sub-area. And you can see our best performer in terms of overall accuracy at 98%, which is pretty good. That's produced by the faults and the gravity and the mag data. So you might expect, it's common sense, that would be the best performer. But what we see here is the MPMs based on the entire superior. And you can see that the accuracy and the out-of-bag accuracy is a lot lower. And with the mag lineaments that I showed you, it's even lower. So our best models are coming from the Abitibi area. Okay, in terms of validation, again, we can create what's called rock curves. Not the rock we play, but receiver operator curves. And I'm not going to go into the detail of this, but because this is a binary classifier, we can create a confusion matrix where we can tabulate the number of true positive, false negatives, and true negatives. This is whether you have gold or not gold. So what we're looking at here is a perfect predictor, as I said, would be right up the x-axis and across the y-axis. But these models are almost perfect predictors. They're very good. If you look at our best performer, which is the random forest using the mag, fault, and gravity data, you can see that the curve is right up here, so it's almost a perfect predictor. This line here means if we had our plot along this line, that would mean it's no better than random chance. So now on the right, we have what I've already explained to you, the efficiency classification curves. And the main point to get from this is that, again, in cyan, the color, the best predictor is based on the random forest, looking at mag and gravity data and fault data. And it outperforms the knowledge-driven models. If we take 10% of the highest areas and look at how many mines we are predicting, 90% of the mines we predict in 10% of the area. Whereas the figure for the knowledge-driven model is much lower, 50%. Now that's usually the case between a knowledge and a data-driven model. But the problem is you have to have training data, good training data, and you have to have good data for predictor maps. So it's data dependent, right? So that's so important to realize that. Machine learning is just a tool to help us. It's not the end all to be all. Here's our final map, and what we've done here is we've taken the top 15% of the most prospective areas for gold, and the magenta area, or the purple area, is where our knowledge-driven model and our data-driven model overlap. And then the green areas are indicative of either its high potential based on the random forest or high potential based on the knowledge-based model. And you can see quite clearly here, again, we predict along the Destor-Porcupine and Cadillac-Larder Lake Fault, we predict this zone fairly well. But again, I draw your attention to other areas where there are very few or no known occurrences up around the Casa Berardi Fault and this fault here. So that's the advantage of this technique. It narrows down our area of exploration. Not a target map, but just narrows down the area of exploration. It still warrants going out in the field and looking at some of this data. So we've worked in 2 dimensions. What about 3 dimensions? What are the expression of these faults? Well, we collected a lot of 3D geophysical data: susceptibility, conductivity, gravity density. And I'm going to show you two areas. The one area is the Larder Lake, which is fertile, for lack of a better word, versus the Swayze, which is less fertile. Now, I realize that the new Cote deposit, well, it's not that new, but it may change how we view the Swayze Greenstone Belt. So let's compare these 2 belts, shall we? And just to show you that some work has been done by the Swayze, some really good work by Francisca Mapia and Richard Smith, as well as some of the data I worked on way back in 2000. Just shows you that we've created these mineral prospectivity maps. And again, if we look at the curves here, very good performance. This is from my colleague Hamming Liu, who used to work with us at Metal Earth, but he's since gone back to China, and this is the work he's done in the Larder Lake area. Again, this banana-shaped curve indicates a very good model, plus the accuracy here is over 90%. So here's what the transects look like, the seismic transects. So we're going north is in this direction, south is in this direction. And this was done by one of my co-authors, Mustafa, and he interpreted faults from the seismic data. And I'll bring to your attention, it appears that the faults, the interpreted faults, are much deeper in the Larder Lake area here, down to around 35, 36 kilometers. And the Greenstone Belt appears to be much deeper as well, compared to the Swayze, where the faults seem to be less deep, if you like, and the whole Greenstone Belt seems to be more shallow. So in summary, I'll let you read this for yourself. The main takeaway, I think, is our results were best with the Abitibi area because we had that clustering bias. And so by using the knowledge-driven model, we can get around that. And looking at the sub-area is another way to look at it. We've confirmed what's already known, that these trending faults are important, okay? And we also are looking at the vertical derivative as being a very important predictor as well. Now, we focused on faults in some of the geophysics. We haven't included geochemistry. We haven't included any lithological information. Certainly, if we included those, we'd probably get better results. So this is where we speculate. Based on the newly collected seismic data, we speculate, and I put that in bold, that the Larder Lake Greenstone Belt is more fertile than the Swayze Belt, due in part to more deeply penetrating faults, which provide conduits for gold-bearing fluids from the lower crust or mantle. It also appears that the Swayze Greenstone Belt is much more shallow. So perhaps this has meaning in the equation with respect to fertile versus non-fertile. And that's it.